First, want to introduce a Grandmaster Tetris player. Yeah.
Hello.
She's working on CAD software in Bevy, and she founded Leapwing Studios together with one of her other speakers, Alex Cecile. And I want to introduce you, Rose Peck.
Thank you. The Tetris thing is real. I do want to warn everybody before we start, this talk includes audience participation. So, there they go. So the extroverted among us can prepare themselves to participate when the time comes and yell answers to my questions when we get there. But today, we're talking about floating point hashing. We're talking about why you should never do it and why I decided to do it anyway. By the end of today's talk, we will hopefully all have learned some new, mildly cursed information about everybody's least favorite number format. But first, I want to talk a little bit about some problem context. I originally gave this talk internally at my day job at the Foresight Spatial Labs, because this came up in a real-world problem that we had to solve: rasterizing non-uniform points. We had a geospatial point cloud, which you can see in the top left there. And this point cloud was tagged with a bunch of different attributes, which you can see I've shown in different colors. The point cloud came from a set of real-world engineering data, but due to an NDA, I can't say exactly what the data was, but like, for example, this may have been particles generated from erosion data on a riverbank. So sediment erodes away from a riverbank, and then we make a point cloud of all of the particles that eroded away, labeled with what kind of sediment it was, when it eroded, that kind of thing. It wasn't that exactly, but that gets us the right idea for the type of problem we're trying to solve. The spatial distribution for our point cloud was relatively uniform, but it wasn't entirely uniform, and we wanted to uniformize it. Essentially, we wanted to rasterize this point cloud to a set of uniform voxels that had the right material tagged on it. And you can kind of see what that looks like here on the right. If you're in the back, it might be a little hard, but this is a bunch of uniform voxels, and they each are colored based on what material composes them. And I want to note that this is non-trivial to do. Since the particles aren't distributed uniformly, a single voxel might contain multiple points, it might contain no points, it might contain only one, we just don't know. So to solve this, we use a Voronoi tiling to determine how much of each particle should be in each voxel. And this is like a relatively standard approach for doing this sort of thing. Here you can see I have a kind of graphic that I made for this. Please appreciate it. I spent way too much time on it. Thank you. It means so much. And here we can see the points from our original point cloud here. So we have one in green, one in yellow, one in red. And then the shaded region around each point corresponds to the Voronoi tiling for each point. So it's the region of space that is closest to that point. And then superimposed on that, I've shown this white grid, which represents the uniform voxels that we're trying to rasterize to. This diagram is in 2 dimensions, but the actual thing was in 3 dimensions. I'm showing it in 2 dimensions because it's easier to understand. Just know that in the real thing, we were doing it, you just do it a third time for the 3rd dimension. The way that the algorithm works is that we check each corner of every voxel to find the nearest point in the point cloud. So for example, if we look at this second voxel here, we take these 4 corners, again in 3D it would be 8, but here it's only 4 corners, we see that each corner is closest to this green point and we mark them as green. If all of the corners of a voxel are the same, then we can map the point and terminate. We can say, okay, all of these are closest to green, this whole voxel can be green, we are good. For another example, we can look at the next block, in the case where they're not all the same. So here we have the same thing, we have our block, we look at our 4 corners, and after we've looked at all 4 of them, we see that 3 of them are green and 1 of them is yellow. The entire thing is not all the same, so in this case, we recursively split into subvoxels and then we check the corners again. Again, normally it would be 8, but here we're recursively splitting into 4 subvoxels. And then each subvoxel has its corners checked. This keeps going until either we reach a subvoxel where all of the corners are the same, like we saw in the first case, or we reach a recursion limit. There is a limit to this, both so that we can keep some reasonable boundaries on the performance, and also to avoid infinite recursion with degenerate cases. But you can see here, these 3 voxels all have green corners, so all of these 3 subvoxels become green. This one is still mixed, so it might keep splitting, or it might stop if we reach the recursion limit. And as you keep doing this, the points that you have checked at each of these corners will slowly approach the true ratio of the contents of the voxel. So that's great and all. But there's something here that I want to point out. These original corners get checked twice in the algorithm. We check them one when we do the first step, and then when we recurse down, we check them all again because they share the exact same geometry because they're covering the same space. And because of how it was written, this ran all of these checks again. And these checks are expensive. You have to find a nearest neighbor point, so that's a BVH traversal, that's big O of log n. And in the actual problem, there were several other things we had to check as well. There were a couple boundary conditions that we had to look for that also took a very long time to calculate. And the performance of this mattered for the case that we were doing this. So I saw this, I saw that these were being done, and what an easy opportunity for optimization, I thought, at the time. We'll just make a cache of all of the points that we've checked so far, and you can see kind of a rusty example of this. We make a hash map, we're starting with our points. These are F64 triples representing the point in space, and then we can map that into the fill that we've computed for that voxel. We can say this one's green, this one's red, what have you. And then I kind of lied over some details here, but when we get there, you take the point and then you try to insert it into your cache once you've computed the value, and then later we can look it up in the cache, and if it's available in the cache, we can skip recomputing it, and we can just get the value from the cache instead of computing it all over again. So this is great. So you code this up and you try to do this, and then the Rust compiler yells at you. It says that you're not allowed to do this. It says that you can't insert the point because F64 doesn't satisfy eq or hash. The trait bounds are unsatisfied. So if you're me, you go to Google the problem, fully expecting that you're going to copy-paste the first solution you find on Stack Overflow. That's certainly what I do whenever I encounter a programming problem that I don't know how to solve. I look it up and I try to copy-paste the first thing that I find. So you do this, you go to Google, and then Stack Overflow yells at you. Stack Overflow also tells you that you shouldn't do this and that this is a terrible idea and this is horribly unstable and you probably don't want to do this. But why? Why can't you hash floats? Why won't it let you? Before we get too deep into this, I want to note that as engineers, I think it's good for us to ask these kinds of questions. Who knows? You could be the genius that proves everybody wrong. More likely, you will learn that everybody else was right and that you were the one that was wrong, but that's still a valuable experience. It helps us learn. It makes us better engineers. So, why? To answer this question, we should first learn a little bit more about floating point itself. So what is a floating point anyway? I assume there's probably some people in the audience that are already familiar with this, but for those of us that aren't, when I was in college, I learned that floating point is a primitive type that's used for fractional numbers and also very large numbers, which the integer types can't handle. So you can do like 0.5, which is obviously not an integer, but you could also do like 15 billion, which is beyond the range of most integers. This is true, but it's also a simplification, i.e. a lie. So today we're going to go a little bit deeper. For our purposes today, a floating point is this. If you look into an F32, if you break it open and you look inside and look at all of the bits that are inside of it, this is what you get. And you see that it's split into three parts. There's a sign component, an exponent, and then a fractional component. You may have heard that floating point works a lot like scientific notation, which is true, except it's in binary. So the way that these three sections are interpreted is like scientific notation, but for binary. The sign bit here is just indicating whether it's positive or negative. In this case, a sign of 0 indicates a positive number. Then we take the fractional portion and we say 1 point that fractional portion in binary. And then we multiply it by 10, but this is 10 base 2, so it's actually 2 in base 10. And we raise that to the power of the exponent, interpreted as a signed integer. In a format that we're more familiar with, it looks like this. So if you look at it in base 10, 1.01000 is 1.25 base 10, times 2 base 10, 10 base 2 is 2 base 10, raised to the power of negative 3, and if you do the math, that results in this. Congratulations, we've made a floating point. With this understanding, we can start to see some problems with hashing. Problem the first, inherent precision loss. There's only 32 bits that we have available here, but we're trying to represent every real number. That means that many numbers, uncountably infinitely many numbers, as a matter of fact, can only be represented approximately. You can't get them perfect. And this is unintuitive. Can anybody tell me what this code outputs? I warned you there would be audience participation. We're taking the number 16,777,214 as an F32, and we're just going up by ones each time and printing each one out as we go. So, and I'll give you a hint, this is a trick question. Who thinks they have an answer? Who wants to try? Yeah, you. Go.
So the first three lines will output what we would expect. The last line will output what we would expect. But the second to last line, the 17, will be truncated towards down. So it will output 16 instead of 17.
That's amazing. Huge congratulations. That's truly incredible. Because this is insane. Absolutely. This is ridiculous. Most people would not know this. I did not know this before I made these slides. Why is this one wrong, but all of the other ones are right? There is a reason for this. I can explain to you the reason for this, but I'm not going to. We're moving on. So that's a problem. This is our list of problems, and we're going to build up this list as we go, but that's one problem. We found one so far. Not every number can be represented exactly, and it's not intuitive as to which ones can and which ones can't. Unless you know exactly what you're looking for, all of those integers look the same to most people. And this can cause issues for hashing. When you're trying to hash a floating point value, it's very easy to hash one number, but actually hash something else. You might think that you're hashing that 217, but the internal representation is actually slightly different. And I know what you're thinking, but don't worry. It gets worse because of drift and error. You see, this limitation on precision is baked into the format itself. This means that every single intermediate value in every mathematical expression is susceptible to this kind of problem anytime you do math with floats. And here's an example of that, and I won't make you guess it because you have no chance. Here we're taking pi, an approximation of pi, and then we add Euler's constant, and then we subtract it again. Mathematically, this operation is the identity. We're taking a number, we're adding another number, and then we're subtracting it again. We should end up exactly where we started, but we don't. You can see that our value ended in 2.5 and now it ends in 2.7. It's actually drifted very slightly from where it began, even though we should have ended up right where we were at the beginning. And to make matters worse, this error can accumulate arbitrarily. Given a long enough mathematical expression, there is no bound on how far your values can drift from where they started. And this has even been used on purpose for some computational clownery. You can see Gradient Half Decent by Tom Seven for an example of that. Very good stuff. Here's another example. Here we're taking 0.1 and we're adding 0.2. Does anybody want to try to tell me what this code outputs? And I'll give you a hint. This is a trick question. That's a really great answer. It's still wrong, though. I'm very sorry. This should actually come as extremely surprising to people who are familiar with floating point, because 0.1 plus 0.2 is a classic example of floating point being wrong. This post on Stack Overflow has 4,000 upvotes. It's a classic problem. You take 0.1 and 0.2, and many people would expect you get 0.3000004. There is even a website dedicated to this problem because of how famous it is. But here we look and it gets 0.3. What gives? What's the deal with this? Did I lie to you? No, the answer is that we're using F32. The classic 0.3000004 error only shows up on F64. It only shows up on double precision floating point. On single precision floating point, it at least appears to be much more correct. Remember when I told you this stuff was unintuitive? I wasn't kidding. So that's another problem. Doing math with our values can pollute them permanently, as we saw in the first example. And as we saw in the second example, the behavior behind how this pollution works is extremely unintuitive, even to people who are familiar with floating point. And, to make matters worse, this error can accumulate arbitrarily. Thinking back to our original problem, this causes a lot of issues for hashing. You can have two mathematical expressions that should provide the exact same output, but they end up being slightly different because of floating point drift. This makes it extremely easy to end up hashing two different values that you think are the same, that should be the same. That's very bad. But I know what you're thinking. Don't worry, it gets worse because of NAN. Remember those edge cases from earlier? When I was going over how floating point works, there was actually several edge cases that I glossed over, and it's time to talk about them now. One of those edge cases is NAN. NAN stands for not a number, and it's a special value which is built into the floating point format itself to handle errors. Invalid operations will result in a NAN value instead of throwing an exception, though that also happens too sometimes. So for example, here we can see some NAN error handling. We can take 0 divided by 0, which is a mathematically invalid operation. You can't divide 0 by 0, and so we get a NAN output as the first one. And then also basically any operation that involves NAN itself is also going to result in a NAN. So if you take NAN and you multiply it by 100, you also get NAN. Great. As another example, we could take 100 and divide it by 0. Division by 0 is mathematically invalid, and so that should result in a NAN, which as you can see, it does. Not just kidding. I guess floating point knows better than me. My bad. I can also explain this, but I'm not going to. So when you look inside and look at what a NAN is, this is what they actually look like. Any floating point value whose bits follow this pattern is interpreted as NAN. If you remember from a handful of slides ago, this is having the exponent portion be entirely ones, and then everything else is stars, wildcards. And you see, note the wildcards, because there are so many of them, NAN is not a single value. There are billions of different NAN values because there are billions of different combinations for all of those different wildcards. The reason this was done was so that the NAN can encode information about what produced the error. So the 0 divided by 0 NAN that we saw might have one particular set of bits, whereas the NAN times 100 NAN that we saw might have a different set of bits. How would you even hash that? A simple solution maybe is to try to work out what the error was, a simple solution maybe is to try to hash all NANs the same. We say, okay, they're all errors, so we'll just say that every NAN is hashed identically. Except, you can't do that, because NAN is not equal to itself by the original floating point standard. This snippet of text is from IEEE 754, which is the RFC that defines how floating point works, and it says that NAN is always unequal to itself, and it's always non-ordered with respect to itself and every other floating point value. Even if you have two NAN values, which are bit for bit identical, they are still considered non-equal. And you can see that borne out in the Rust here. NAN equals NAN, false. As a bonus fun fact, if you actually try to do this in Rust, the compiler yells at you because this is not a valid way to compare NANs. As a doubly bonus fun fact, I'm pretty sure this is the actual reason why eq, ord, and hash aren't implemented for floats in the standard library. Because NAN is not equal to itself, because NAN is not equal to itself, you cannot create a mathematically consistent definition for any of these traits. So, that didn't work, but maybe there's still a way? NANs are encoding error information, so perhaps we could try to figure out which error the NAN is indicating, and then we hash based on that, similar to what we might be familiar with a result, where different error variants could all get different hashes. That should work, right? Wrong. You can't do that either. Again, in the original definition, we can see here that the exact bits that are encoded is left to the implementer's discretion. Which bit strings correspond to which errors, and even which errors are encoded at all, is left undefined by the IEEE standard. Different chip manufacturers are left to do this however they wish. So if you try to hash exact bit values, you will get different behavior on different platforms. That's really bad. NAN really throws a wrench in things because of all of the edge cases in its definition. And that's not even including all of the other stuff that I cut for time. Things like transcendental functions, the fact that absolute accuracy goes down as you get further away from 0, the fact that LLVM can optimize out certain operations, further obfuscating which operations are occurring to your numbers, value casting, the special case infinity values, the fact that floating point has both positive and negative 0, and these are definitionally equal to each other despite having different bit strings, subnormal values, all of these things cause problems for hashing. There is no sensible hash implementation for floating point. You cannot do it. But what are they gonna do, huh? Take me to floating point jail? What's the worst that could happen? As my coworker pointed out when I originally gave this talk at work, the standard library provides this 2-bits function. We can just use it. And we do have some advantages here. Let's think back to our original problem. We're only trying to implement a cache here. We're not trying to make a general purpose hashing system. This is kind of a big deal. We only want to look up values that we've already computed. In a cache, false negatives are inefficient, but they don't result in any incorrect values. Suppose, for example, that we have some point in space, point A, and we hash it twice. But for some reason, we get two different values. For all of the myriad reasons that we've discussed, when we hash a point A the first time, we get one hash, but when we hash point A the second time, we get a different hash. The second hash will miss the cache, but that's fine. We'll end up recomputing the value unnecessarily, but the only thing we've lost is wasted time. This means that overly conservative hashing, while it leaves money on the table, it is safe to do in general. This is a huge win. It doesn't solve all of our numerical stability problems, but it does give us a lot of slack that we can work with. Okay, great, but what about all that NAN nonsense? As it turns out, we have a handful of advantages here as well. Because of our problem domain, NAN doesn't really matter. We're working with real engineering data here, mostly measurements that are from an actual site that were measured by an actual human. NAN should never occur. Even if it did, our system would already be hosed. We're doing a bunch of other math, and all of that other math that we're doing can't properly handle a NAN value either, so any weird NAN behavior that's introduced from the hashing system is no worse than anything that we're already doing. Garbage in, garbage out. So, maybe there's a way. We don't need to worry about the false negatives, where the same value gets two different hashes, and we don't really need to worry about the weird values either. So what about false positives, where two different values end up getting the same hash? This could occur if you have two values that drifted into each other, converging on the same incorrect value. Well, there may be a way to handle this. We know the devil. We know our problem domain very well. We're specifically trying to rasterize these non-uniform points, and that means we can make some assumptions about our data. Based on the scan area, we can put an upper bound on the total size of our point cloud. Again, thinking about scanning riverbanks, we're dealing with a dataset that's not going to be kilometers wide, we're dealing with something that's meters wide. Very unlikely it would ever be more than, say, a few hundred meters. We can assume, for example, that all of the voxels that are coming into our function are a uniform 1 by 1 by 1 cube, which was true in the original problem and is true in the toy example here as well. We know that the recursion depth of our function is bounded, which means that we know that our subvoxels can only get so small before we give up and terminate, and so on, and so on. All of this means we can get some pretty accurate bounds on the scale and distribution of our data. Additionally, we know what math is happening to those numbers. And all of that means we can get some reasonable bounds on the error of our numbers. If we can bound the accuracy of our values, we can be pretty confident that we're not going to get any false positives on our cache, which means we did it. And that means we can look at the actual implementation that I wrote. This isn't the literal implementation, this is a slightly simplified version, but it's essentially the same idea. It's a little bit complicated here because we're doing a bit of bit magic to perform a ULPS comparison. I can talk about that if people are interested, but if not, I'm going to kind of just gloss over that for time. The important takeaway, though, is that we're treating a small neighborhood of consecutive floating point values as being identical for the purposes of hashing. In this case, it's every 4 consecutive values. This is done on purpose. The idea is that we want to be a little bit fuzzy in order to handle errors and to reduce the number of false negatives, but we don't want to be so fuzzy that we then start getting false positives. And I did a bit of math to try to come up with a reasonable boundary here. And given the boundary on the accuracy of our data, we can do this with some reasonable safety. And that's about it. Dear Princess Celestia, today I learned that floating point hashing is bad and you should not do it, that even if you think you know what you're doing, you probably don't, but sometimes, if you can put enough constraints on your problems, you can justify it and you can do it safely. What a nice talk. Do you buy it? Because I'm not sure that I buy it. Looking at this code again after the lapse of almost a year, over a year, there's actually a couple of things that I missed. Can you spot the errors at home? I won't make you shout it out because we're starting to run up on time. The main thing that I noticed was that I didn't really account for arbitrary error accumulation properly when I wrote it back then, and I also didn't really account for subnormals. I can get into this if people are curious, but I'm going to keep moving. Knowing what I know now, I could probably justify that all of these issues are actually fine. I still stand by the hash implementation that I wrote. I don't think that there is a problem with the code. I think the problem was in my proof. And that's not great. I probably could justify some of these things, but when I wrote it, I didn't properly justify them, and I really should have. So let's try that conclusion again. Dear Princess Celestia, today I learned that we don't know the devil, and you should be afraid of floating point, because even if you think you know what you're doing, you probably don't. Thank you very much for your time.
Thank you so much, Rose. That was lovely. Do we have any questions in the audience? Do you want to run around over there?
Perfect.
So you only showed the hash implementation, but what about the equals implementation?
That's a great question. The EEC implementation, I can actually go, the slides are gone, that's fine. The EEC implementation was done very similarly. It also used the same ULPS trick, but essentially it was done the same way where a small neighborhood of floating point values would all get truncated into the same one, and then you would compare exact bit equality on those. So essentially, if they were hashed the same, then they are equals each other, and if they're not hashed the same, they're not equals each other. And I think that might actually be a requirement in the hash trait that needs to be consistent with EEC. But yes, that is how I did it.
Thank you.
Any other questions?
Okay.
I see something over there. Can we throw?
I'm not particularly excited about throwing.
So, great
But
talk.
it's made for throwing. Nobody will get hurt.
So, great talk, thanks. I noticed in the hash implementation that after converting to the bits, you hashed an array instead of a tuple. Was there some specific reason for that, or was it just random?
No, it was just random.
Okay, thanks.
There is no particular reason behind the array.
You only need to check you're only checking the points on the corners of the raster.
Yes.
And then maybe a smaller raster and a smaller raster, but up to a limit. So why don't you just convert or treat the raster as an integer grid and hash
That's
those?
such a good point. You're extremely correct, as a matter of fact. So when I gave this talk originally at my company, somebody at work asked me essentially that exact same question, and they were very polite about it, as you have been. And I, with some embarrassment, admitted that, well, I didn't really think of it at the time, so I didn't do it. But that is the way that it should be handled. I put a link to my blog on there for shelling purposes. On there, I actually have an addendum post. I post a blog post with a bunch of extra bonus stuff that I couldn't fit into this talk, and that is one of them that I talk about, but I'll briefly go over it here. The point that's being made, because you know the exact spacing of all of the subvoxeling that you're doing, you could actually create a uniform integer grid and then use that. And this is exactly how this should be done. If I were to rewrite it today, I would not write a hash implementation and I wouldn't use floating point at all. I would use a regular integer grid and I would evaluate it on that grid. And then you can maintain a cache, and because integer math is entirely deterministic, including across platforms, you're totally fine. So very good point. Yes, you should do that. Don't do what I did.
All right, let's have a final question.
I think it's a very similar question, but the question is also, can we convince people in industry not to use floating point when capturing data?
I've tried. I have tried, but I don't think so. That being said, I don't think it's terrible. I talk about this in the blog post a little bit as well, but for real-world engineering data, I don't think it's a bad format. There's a ton of trade-offs that were made, and if you read through the whole RFC, you can really feel the trade-offs being made. Things about relative accuracy preservation, things about being able to handle different orders of magnitude. I think that for real engineering data, it's not a bad format. And as we kind of saw in the talk, a lot of its quirks sort of just come out in the wash when you're using it for its original intended purpose. That being said, I don't think we can convince industry, even if maybe we should. And as somebody who does build industry software, they mentioned I do write CAD software for a living. I'm generally of the opinion that fixed precision systems are usually better if you can, because if you know what domain you're working in, you can usually make a pretty reasonable guess at what precision you need to be working in. Going back to the riverbanks example, if you're looking about spatial data that's on the scale of a riverbank, you can be pretty confident that anything you're working with doesn't need anything more than, say, micrometer precision. That if you're precise down to a micrometer, any user would be happy with that, even if you, even if you don't have perfect relative precision all the way down to the subnormals.
All right. There were a few more questions. I think you can find Rose around.
I'll be around. Maybe out in the hallway. I don't know.
Thank you so much. Let's give it up for Rose.
Thank you.